Black hole. What's more complicated, less understood, extremely more interesting than black holes? In this lesson, I will show how black holes are formed and die in the formation of stars, Hawking radiation, extragalactic jets, and finally, the result of an article review entitled Powerful Extragalactic Jets Dissipate Their Kinetic Energy Far from the Central Black Hole. We now know that stars are massive gaseous objects that contain mostly hydrogen atoms that collapse under their own gravity. In their core, hydrogen atoms are fused together to form helium in the process we call nuclear fusion. This process releases incredible huge amount of energy that pushes against gravity. A balance exists between these two forces until fusion occurs in the core. But for massive stars, way more massive than the Sun, fusion creates heavier elements up to iron, where fusion process does not anymore produce energy. Since iron is so dense, gravity builds up that surpasses radiation. The core collapses, and core feeds all of star masses. In just a fraction of a second, the star explodes, releasing all elements therein into the universe, leaving either a neutron star, or, if it is massive enough, a black hole. In quantum field theory, a vacuum is not actually an empty space, but is boiling with quantum fluctuations, creating a matter and antimatter that lives only for a very short time before annihilating each other. When this happens near the event horizon, one particle falls into the black hole while the other escapes. We call this the Hawking radiation. Ultimately, these radiations must come from the black hole. So, over a very long period of time, the mass of the black hole decreases until it explodes. If you look at the black hole, what we're really seeing is the event horizon. Anything that crosses the event horizon needs to travel faster than the speed of light to escape. In other words, impossible. If the black part is the event horizon, then what is this part? As of now, nobody knows. Does it have dimensions? What is it made of? If it's a singularity, then it is a division by zero, so it's complicated. Theoretically, anything can be converted to black hole by simply compressing them to proper Schwarzschild radius, or the distance from the singularity to event horizon, which can be calculated by this equation. Most of the galaxies we observe are considered normal. We inhabit a normal galaxy called Milky Way. In normal galaxies, light comes from the stars in it and is distributed approximately uniform, but some galaxies release intense light and even invisible radiations from their nuclei. These are active galaxies. Most of these galaxies release incredibly huge amount of energies, both in the invisible and non-visible radiations, mostly gamma rays. There are four types of active galaxies: Seyfert galaxies, quasars, blazars, and radio galaxies. Seyfert galaxies are active spiral galaxies. Its nucleus has bright emission lines of both visible and invisible radiations. The nuclei of such galaxies have been observed to change every few weeks, suggesting that the center must be relatively small, about the size of the solar system. Quasars are extremely luminous, energetic, active galactic nucleus with centers so massive, at least a million times massive than our Sun. Their luminosity varies more frequently. The word quasar came from quasi-stellar radio objects. Blazars are basically just quasars. Quasars going directly towards Earth are called blazars. Radio galaxies are those that emit radio waves. They are elliptical and emit jets above and below the galactic center. All of these activities are now known to have been driven by supermassive black holes. But where exactly do they come from? Do they come from the black hole? Well, that will bring our great Stephen Hawking from there, since we know that only a Hawking radiation escapes from black hole. I reviewed an article that studied just this phenomenon: powerful extragalactic jets from the center of active galactic nuclei. This was taken from the journal Nature.com and was written by Adam Leigh Harvey and his professor. Attracted by a very strong gravity, matters fall into the central black hole as it feeds on the surrounding gas and dust. But instead of falling into the black hole, some particles accelerate close to the speed of light and shoot out in two narrow beams. These form when inner accretion disks spin faster than the outside ones. This speed differential causes magnetic field to cold out, ejecting the materials falling into the black hole at nearly the speed of light. The blue lights you see are electrons spinning so fast in a process called synchrotron. The spectral energy distribution, or SED, of an extragalactic jet is well described by a general two-peak structure with a low energy component peaking in the infrared due to synchrotron emission of the relativistic particles in the jet. In powerful jets, the high-energy gamma-ray component dominates over the low-energy component and is the main outlet of energy dissipation, while the seed photons for inverse Compton scattering are thought to be external to the jet. That is why this mechanism is termed external Compton scattering. Different methods of localizing the gamma-ray emission had been performed before. Short variability timescales of gamma-ray emission in powerful jets has been used to argue that the dominant emission site must be on the sub-parsec scale, implicating the broadline region. The broadline region is opaque to very high energy gamma rays, and tera-electron volt detections of powerful jets have challenged the broadline region scenario. A lack of absorption features in the total average gamma-ray spectra of Fermi LAT detected powerful jets also changes this scenario. In contrast, several simultaneous gamma-ray optical flares in which the optical emission exhibited polarization behavior similar to that of the very long baseline interferometry. Radio emission implicates an emission site at or near the broadline region beyond the molecular torus. Due to this, Adam Harvey developed and applied a diagnostic of the location of gamma-ray emission, which is dependent on these observable quantities and which can be applied to a large sample of sources, avoiding errors. He called it seed factor. Since this technique only used observable quantities, then this is a robust technique. 4 samples for seed factors came from the peak frequency and peak luminosity of both synchrotron and inverse Compton or external Compton scattering. Data used are actually available in database and previous studies. 2 of these samples are catalog samples from the literature with SEDs published in their respective papers. One of these 2 samples is made up of 5 different subsamples selected based on different criteria in a project of the Planck collaboration. The second is the Fermi LAT bright AGN or active galactic nucleus sample. The third is from sample of blazar SEDs for some sources observed in the tracking active galactic nuclei with Austral milliarc second interferometry program or TANAMI. The fourth sample is a sample of SEDs taken from a literature search of 2 different well-observed sources. In other words, the problem just sits in front of scientists with all the data available hiding in plain sight, and it took a PhD student to see and solve them. Fitting of the obtained sets in the model was performed using maximum likelihood regression implemented through a simulated annealing optimization algorithm. Errors were calculated using likelihood ratio method, the Wilks theorem, implemented through a combination of bootstrapping, kernel density estimation, and polynomial interpolation. Seed factor and standard deviations for these 62 SEDs were also calculated. To test the normality of seed factor distribution, 2-sided bootstrapped Kolmogorov-Smirnov test was performed using a rejection significant threshold of twice the standard deviation. The results showed that the normality of the seed factor distribution cannot be rejected significantly. The model must also be tested by comparing the seed factor distribution of powerful extragalactic jets with that of weak extragalactic jets, which are known to emit through processes other than external Compton. The distribution for powerful jets was found to be different than that of weak jets, further implying an external Compton origin of the emission from powerful jets. This is a histogram showing the distribution of seed factors for the sample of flat spectrum radio quasars. This is the kernel density estimate of the seed factor distribution of the combined sample of 62 SEDs. The KDE is plotted as a thick black line. We can see a normal distribution. Result argues that the broadline region is not the dominant location of gamma ray emission. The fact that the seed factor distribution has a peak, and this peak is around the molecular torus seed factor. Thus, after fitting 62 quasi-simultaneous SEDs, Adam and his team concludes that the molecular torus is strongly preferred as a dominant location of gamma ray emission. This demonstrates that energy dissipation in powerful galactic jets occurs at about 1 parsec downstream of the supermassive black hole. Therefore, powerful extragalactic jets dissipate their kinetic energy at about 1 parsecond from the central black hole, or to about 10,000 Schwarzschild radii for a black hole 1 billion times more massive than the Sun.